Welcome back, everyone. Ready to dive into something pretty fascinating.
I'm ready. Let's do it.
Today, we're looking at this paper on Kato's square root property for the generalized Stokes operator. Now, I'm sure a lot of you are already familiar with Kato's conjecture from way back in the 60s.
Oh, yeah.
It seems so simple, right? A question about the square root property of these operators in Hilbert spaces.
Well,
But it really kept mathematicians busy for, well, decades, really. And this paper, they're claiming they finally cracked it, at least for the generalized Stokes operator, that is.
right.
And the techniques, gotta say, they're pretty groundbreaking.
Absolutely. This is a big deal. And, what makes it even more exciting, it's not just some abstract mathematical victory. This actually matters in the real world.
Right.
The generalized Stokes operator. It's crucial in fluid mechanics, especially when you're dealing with non-Newtonian fluids. All that complexity.
Exactly. So before we get, too deep into the weeds of the actual proof itself, let's make sure we're all on the same page here.
Yeah.
About the key players, I mean.
Sounds good.
So the generalized Stokes operator, what is it that makes it so special? And why is it such a pain to work with?
Well, think of it this way. The generalized Stokes operator, we often use $8 to represent it, can be expressed as $1 be a nebula. Now, dollar, that's a matrix of bounded measurable coefficients.
Okay, so far so good.
And these coefficients, they represent the fluid's properties, like viscosity, for instance. And the thing is, viscosity, it can vary from one point to another. It's not always the same everywhere.
Right.
So that's what makes this operator generalized. It takes those variations into account, you see. Unlike the classical Stokes operator, that one just assumes that the viscosity is constant, which, let's be honest, isn't very realistic.
Yeah, that makes sense. So those bounded measurable coefficients are kind of like the wild card, right? They capture all the non-Newtonian weirdness we see in real fluids.
Yeah, exactly.
But why does that make the operator so tricky to deal with mathematically?
Well, you see, these coefficients, they can get messy, like really messy, discontinuous even. And that really throws a wrench in a lot of our standard tools. The ones we usually use for analyzing elliptic operators, they often depend on things being nice and smooth.
Okay, so basically all the approaches that work perfectly fine for those well-behaved operators, they just sort of fall apart when we have these unruly coefficients thrown into the mix.
Exactly. And that's where this paper's brilliance comes in. They found a set of techniques that can deal with that lack of smoothness, head on even.
Okay, I'm intrigued. Let's talk about those techniques. The paper mentions something called non-local off-diagonal estimates. What's the story there?
All right, so these estimates, these are at the core of their whole approach. They provide a way to control how the operator behaves, even when you've got those discontinuous coefficients causing trouble.
I see.
But to really understand them, we need to think about off-diagonal decay for kernels of operators. Remember that?
Yeah. It's the idea that the kernel's influence should fade away as you move away from the diagonal.
Right, exactly. Think of it like this. Changes in one part of the fluid, they shouldn't have a huge impact on areas that are far away.
Right, yeah, okay.
Now, traditional off-diagonal estimates for elliptic operators, they really rely on the operator's locality, but the generalized Stokes operator, thanks to those variable coefficients, it's different. It's non-local. Changes in one spot, they can actually have effects far away.
Oh, interesting. So they had to find a way to capture those long-range interactions while still, keeping the operator's behavior under control somehow.
Exactly. That's the whole non-local aspect of these estimates. They've come up with this framework that, it quantifies how the operator's influence decays with distance, even when you don't have strict locality.
However, how do they do that, though?
Well, they use something called a Cacciopoli inequality, but they adapt it to the non-local setting. It's a modification of the classical one that's usually used to bound a solution's energy in a region by its values on the boundary. But their version, they've got this extra term, it accounts for those non-local interactions we were talking about.
So it's like they added in a kind of correction factor to the classical inequality, right?
Precisely, to take into account those far-reaching effects.
Yeah.
And from that non-local Cacciopoli inequality, they get those key off-diagonal estimates. The estimates show that the operator's kernel does decay, even if it's slower than in the classical case, as you move away from the diagonal.
Okay, that's pretty cool. So they're basically saying even though the influence doesn't vanish as quickly as you'd think for a local operator, they can still control the decay, and that's the key.
Exactly. And those non-local off-diagonal estimates, they are the cornerstone of this whole approach to tackling the square root property.
All right, so we've got those estimates. What's the next piece of the puzzle?
Next up, we've got what they call the principal part approximation. Think of it like this. They split the operator up into two parts. You've got the good part that behaves nicely, and then there's the bad part. That one's all the headaches from those variable coefficients.
Feels like a classic divide and conquer strategy.
You got it. They basically make an approximation of the original operator. They replace those tricky coefficients with a constant matrix. And that simplified version, no spatial variations, so it inherits the nice properties of the classical Stokes operator.
Okay, so they're kind of smoothing out the rough edges to get something a bit easier to handle.
Precisely. But, and this is the tricky part, they then have to analyze the error that they introduce. They need to show that this bad part, the difference between the original and the smooth version, that it doesn't mess everything up.
Right, otherwise their whole strategy just, poof, goes up in smoke.
Yeah.
So how do they control that error?
That's where those non-local off-diagonal estimates come back in.
Ah, I see.
They use them to set bounds on the bad part, showing its influences, well, it's tamed enough that the whole proof can still work.
Okay, they've split the operator, they've got the error under control, and they've got these powerful non-local estimates. What's the final ingredient that brings it all together?
The last piece. It's a special test function. They call it QTA$, and it's designed very, very carefully to capture how the operator acts in a certain direction. The direction's given by a unit matrix $.
Okay.
It's a delicate balance, though. This function, it has to be divergence-free, because of the incompressibility of the fluid, but it also has to be really concentrated in that theta direction.
Divergence-free and concentrated in a specific direction. That sounds challenging. How did they manage to construct something like that?
Well, they use something called the Bogovsky correction. It allows them to take their initial design, which is based on a convolution with the smooth cutoff function, and tweak it. Make sure it's divergence-free while keeping that concentration.
So it's like a fine-tuning step. Make sure everything plays nicely with that incompressibility thing.
Exactly. And with this test function, they can get a crucial Carlson measure estimate.
Hold on. Remind me about Carlson measure estimates. What are those all about again?
They're a way to quantify how concentrated something is. Like, imagine how densely stars are packed in a certain part of space, that kind of thing. In this case, the Carlson measure estimate, it helps them control the behavior of the operator's square root.
Okay. So it's like they're using this measure to make sure that the operator's square root doesn't go haywire with, crazy fluctuations or concentrations.
Precisely. And that Carlson measure estimate, combined with their work on the non-local off-diagonal estimates and the principal part approximation, that's the basis for proving Kato's square root property for this generalized Stokes operator.
Wow, it's like they've woven together this whole tapestry of really sophisticated mathematical tools to make this happen. I'm definitely eager to see how they use this Carlson measure estimate in the final steps. But I think we've covered a lot already.
We have.
Maybe we should take a break and come back to it. Pick up the thread in the next part of our deep dive. What do you think?
Sounds like a plan. We've laid the groundwork. Now we just need to see it all come together.
All right, let's pick up where we left off. We've got the stage set. We've met the main players. The generalized Stokes operator, those non-local off-diagonal estimates, the principal part approximation. Oh, and that really carefully made test function.
Right.
Now, let's see how all of these pieces fit together to actually prove Kato's square root property.
Okay, so remember, the core of Kato's conjecture, it's about showing that the domain of the square root of the operator, we usually denote that with mathcal, well, it's got to be the same as the domain of the gradient operator. That one's in mathcal. And not just the same, the norms have to be equivalent too.
Right.
So, putting it simply, if you take the square root of the generalized Stokes operator, does it behave, well, nicely? With respect to taking gradients.
And by nicely, we mean applying the square root of the operator to a function. It shouldn't lead to any, weird blow-ups or crazy behavior compared to just taking the gradient of that function.
Exactly. Now, proving this equivalence, it usually comes down to, to proving two inequalities. The first one, it's pretty straightforward. You got to show that the norm of square, it's bounded by the norm of no below. Basically, applying the square root of the operator, it can't be worse than taking the gradient.
Got it. So that first inequality is like setting a limit, right, on how crazy the square root of the operator can get.
Yeah, think of it like an upper bound. Now the real challenge is proving the other inequality, the reverse one. You have to show that the norm of no below is bounded by the norm of squaro. This proves that the square root of the operator is strong enough, so to speak, to really capture the essential behavior of the gradient.
Okay, so we need to show that the square root doesn't miss out on any important information compared to taking the full gradient.
Exactly. And that's where those ingenious techniques we talked about earlier, they really come in. The non-local off-diagonal estimates, that principal part approximation, and that special test function, they all work together to prove that reverse inequality.
All right, let's walk through how they do that. I'm really curious about that Carlson measure estimate. How does that fit in?
Okay, good question. Remember that special test function? QTK dollars, divergence-free, concentrated in the direction of that unit matrix?
Yeah.
They use this test function to connect the norm of W to this integral that involves the square root of the operator applied to do.
Okay, hold on. How do they make that connection?
Well, they use the fact that QT is divergence-free. It lets them rewrite the integral, the one with W in it, in terms of the operator over applied to 2. Then, with some clever integration by parts and using the properties of that test function, they transform it into a form where you have score.
So they're basically manipulating the integral using their special test function to get the square root of the operator to show up.
Right. And the really neat part is that this transformed integral can be bounded by a Carlson measure. And this Carlson measure, it involves quarter. That's where the Carlson measure estimate comes in.
Right, right. It provides a way to control how concentrated the square root of the operator can be.
Exactly. And because they connected the norm of W to this Carlson measure with Skoric, they've basically established that reverse inequality we were after. They've shown that the norm of W really is bounded by the norm of Swart.
So by choosing their test functions so carefully and then using this Carlson measure estimate, they're able to bridge that gap, right, between the gradient and the square root of the operator.
You've got it. And that's basically it. They've proven Kato's square root property for the generalized Stokes operator.
Wow, what a journey. They've taken some really deep ideas about how this operator works and combined them with these powerful mathematical tools to overcome those tricky variable coefficients.
I know, it's impressive.
It's a real testament to how creative these mathematicians are.
Absolutely. It's a huge achievement. It opens up all sorts of new avenues for research, both in abstract operator theory and in fluid mechanics.
Speaking of fluid mechanics, let's shift gears a bit. Let's talk about what this result means for understanding real fluids, especially those non-Newtonian ones. They're so fascinating.
Yes.
But maybe we should save that for the last part of our deep dive. What do you think?
Yeah, I think that's a good idea. We've tackled the proof. Now let's see what it means for the real world.
Okay, so we've gone through this intricate proof, right? We've looked at the history of Kato's square root problem. And now it's time to see how all this math, how it shines a light on fluid mechanics. You know, the generalized Stokes operator, it's really at the heart of understanding how fluids behave, especially those complex non-Newtonian ones.
Absolutely. Proving Kato's square root property for this operator, it's huge. It really solidifies our theoretical understanding, for analyzing these equations that govern how fluids flow. And especially when you're dealing with those tricky variable coefficients that capture that non-Newtonian behavior.
Right. Those variable coefficients, they're representing things like viscosity, right?
Yeah.
And viscosity, it can change depending on the fluid state. That's what makes non-Newtonian fluids so interesting and challenging, of course, to model.
Exactly. Think about things we see every day, like ketchup or toothpaste, even blood, actually. Their viscosity, it's not constant. It changes depending on how much force you apply. That's why ketchup can seem, almost solid in the bottle, but then it flows easier when you give it a good shake.
Ah, so those sudden changes in viscosity, that's what those variable coefficients in the generalized Stokes operator, that's what they're capturing, right? That's what makes these fluids behave in such unexpected ways.
You got it. And mathematically, those variable coefficients, they add a whole other level of complexity. The traditional ways of looking at fluid mechanics, they struggle with that.
So how does proving Kato's square root property for the generalized Stokes operator, how does that help us tame that complexity?
It gives us this crucial piece for analyzing the well-posedness of the equations that govern fluid flow. To put it simply, it helps us know if these equations actually have solutions. And if those solutions, if they exist, if they're unique, and if they depend, in a continuous way on the initial conditions and the boundary data.
Okay, so that makes sense. Those are the things you'd want in a good mathematical model, right? To make sure that the solutions actually have a physical meaning and that, little changes in the input don't lead to crazy different outcomes.
Exactly. Establishing well-posedness, it's essential for theoretical understanding and for practical applications. It gives us confidence that, that our models are reliable, that the solutions we get, they actually reflect what's happening with these fluids we're studying.
So proving Kato's square root property, it gives us this stronger theoretical grasp on these non-Newtonian fluids, right? And that paves the way for better models, more accurate, more reliable. Can you give us some specific examples of how this result might actually change our understanding or lead to new applications in fluid mechanics?
Sure. One area where this could have a big impact is in microfluids.
Okay.
That's all about manipulating really tiny amounts of fluids, often in very small spaces. And non-Newtonian fluids, well, they're becoming more and more important in those microfluidic devices. The ones used in things like biomedical engineering or drug delivery or lab-on-a-chip technologies.
Ah, so those tiny devices, the ones working with fluids at microscopic scales, they often rely on non-Newtonian behavior to do their thing. How does this mathematical result fit into that?
It gives us a much more rigorous understanding of the equations that govern those non-Newtonian fluids. So we can design and optimize these microfluidic devices much better. We can predict more accurately how those fluids are going to behave in those confined spaces. And that leads to more efficient, more reliable devices.
It's like having a more accurate blueprint for building those microfluidic systems, right?
Yeah.
Making sure they work the way they're supposed to.
Exactly. And it goes beyond microfluidics, too. Think about geophysics. Understanding how non-Newtonian fluids, things like magma, how they flow, that's essential for modeling volcanic eruptions and, predicting earthquakes.
So this is really connecting some pretty abstract math with, some pretty fundamental processes on Earth.
It is. And then there's materials science. This result, it could help us make new materials with specific, payload rheological properties. That's about how they deform and flow under stress. Non-Newtonian fluids, they're often used when making polymers, plastics, all sorts of materials. So understanding them better, that could lead to real innovations in how we design and process materials.
It's amazing how this math, it seems so abstract at first, how it ends up having such a big impact on understanding the physical world around us.
It really shows how connected all these scientific disciplines are, and it shows the power of math, how it can unlock these secrets of nature. And you know what? This proof of Kato's square root property for the generalized Stokes operator, it's a huge step, but it's really just one step. There's so much more to explore in fluid mechanics.
Absolutely. It's a journey that's going to keep inspiring mathematicians and scientists, for who knows how long.
I agree. And to everyone listening, I'd encourage you to really dive into this fascinating world of fluid mechanics. See how math helps us understand its mysteries. From how water droplets move to that turbulent flow of magma deep beneath the earth, it's all connected. Fluids, they're everywhere. They shape our world. And understanding them, it's not just a scientific thing. It's a journey of discovery. It can inspire awe and wonder.
Well said. And on that note, I think we've reached the end of our deep dive. It's been great exploring this incredible mathematical result and all its implications with you.
It's been my pleasure. And to all our listeners, we'll leave you with this thought. As we keep pushing the boundaries of what we know, math, it's going to be right there with us. It'll light the way, showing us the patterns, the connections that govern everything around us.
Welcome to another deep dive. Today we'll be exploring, I think you'll find it quite intriguing. A paper on Kato's square root property. But with a twist, as always.
Right.
This time it's applied to the generalized Stokes operator. Now, I know our listeners are no strangers to, complex mathematics.
Absolutely.
But what makes this paper really stand out, at least to me, is the challenge of proving this property for a non-local operator.
Yeah.
It's a bit like trying to solve one of those jigsaw puzzles, but where the pieces can kind of mysteriously influence each other from a distance.
Yeah, that's a great analogy, actually. Kato's square root property has a history of, throwing some real curveballs at mathematicians. It can appear, deceptively simple in some cases, but proving it for certain operators can become, incredibly difficult.
Yeah.
And this generalized Stokes operator with its, inherent non-local nature, it definitely falls into that category.
So let's start by just unpacking the operator itself. I know it's used in, modeling the flow of fluids, but what sets it apart from the classic Navier-Stokes equations?
So the generalized Stokes operator allows us to model more complex fluids.
Yeah.
Those that don't behave quite as neatly as, well, water or air.
Okay.
So think about substances like, I don't know, silly putty.
Yeah.
Or ketchup, or even blood.
Interesting.
They have a much more intricate relationship between stress and strain, and that makes their flow behavior a lot harder to predict.
So it's like Navier-Stokes, but on steroids.
You could say that, yeah.
Okay.
So equipped to handle the weird and wonderful world of of non-Newtonian fluids.
I like that.
The formal definition of the generalized Stokes operator is given by this equation.
Okay.
So A represents the operator. A colon equals negative divergence of mu, gradient of up plus gradient of phi, comma, divergence of u equals 0. So where A represents the operator, u is the fluid velocity. Mu is the viscosity, and that can vary spatially. Nabla is the gradient operator. Div is the divergence operator, and phi represents the pressure.
Okay.
Lots of symbols.
Yeah, and the part that really makes this a challenging puzzle, at least from what we've talked about so far, is that divergence of u equals 0 condition, right? That's telling us that we're dealing with an incompressible fluid.
Right.
But how does that seemingly simple constraint lead to non-locality?
Right. So imagine you're pressing on a point in an incompressible fluid.
Okay.
Because the volume can't change, that pressure doesn't just stay localized.
Yeah.
You know, it propagates throughout the entire fluid.
Oh, I see.
And it affects the velocity at very, very distant points. So this interconnectedness, where behavior at one point is influenced by what's happening far away, that's really what we mean by non-locality.
It's really fascinating how such a fundamental property of the fluid can lead to such complex mathematical behavior.
Yeah.
So where does Kato's square root property come into play in this sort of non-local world?
So Kato's square root property, it's at its heart, it suggests a sort of decomposition principle for operators. So it proposes that finding the square root of an operator is kind of like finding the square root of its individual components. If you break it down.
It sounds almost too good to be true.
Right.
Is it always that straightforward?
Well, unfortunately, no. The mathematical world is full of surprises, and sometimes combining those individual components creates something entirely new and unpredictable. And that simple relationship, it breaks down. And proving Kato's property then becomes a significant hurdle to overcome.
And that's precisely the challenge that this paper tackles for the generalized Stokes operator.
Yeah, precisely. The paper focuses on proving theorem 1.2, which asks, is the domain of the square root of this operator exactly the same as the space of divergence-free H1 vector fields? And can we establish the estimate that connects the norms of these two spaces?
I can already sense that the proof itself is where the real ingenuity lies.
Yeah.
What were some of the initial roadblocks that the researchers encountered due to the non-locality of this operator?
So the traditional toolkit for proving Kato's property relies heavily on techniques that are really designed for local operators, where the value at a point only depends on its immediate surroundings. And these techniques they break down when faced with non-locality because they can't account for those for those long-range interactions.
So it's like trying to use a microscope to study the behavior of a flock of birds.
Yeah.
You need a different lens, one that can capture the collective movement and interactions, across the entire flock.
Exactly. For example, one common technique is to divide the space into small regions and analyze the operator's behavior on each region separately.
Yep.
But with non-locality, those regions can't be treated as isolated. They're all intertwined.
I see.
And what happens in one region can instantly affect another.
That makes perfect sense. So how did the researchers manage to overcome these challenges? What new tools or approaches did they bring to the table?
So they had to develop innovative techniques that are specifically designed to handle this non-locality. And one of their key innovations is the use of what are called non-local off-diagonal estimates. And this is described in Proposition 2.5 of the paper.
Those sound intriguing. What exactly are non-local off-diagonal estimates, and how do they help tackle this problem of non-locality?
Right. So these estimates provide a way to quantify the influence of one point on another, even if they're very far apart. So imagine Imagine trying to measure the gravitational pull between two objects. The closer they are, the stronger the pull, right?
Right.
So off-diagonal estimates essentially give us a way to measure this pull in the context of the operator. So capturing how the behavior at one point affects another, even, across large distances.
So it's like they've developed a new ruler to measure distances in this non-local world.
Exactly.
One that accounts for those long-range interactions.
Precisely. And these estimates become crucial for analyzing the behavior of the generalized Stokes operator, and ultimately for proving Kato's property.
I'm really curious to see how they put these non-local off-diagonal estimates to work. But before we dive into the specifics of the proof, could you give us a bit more intuition about the challenges posed by non-locality? Like, what are some other traditional techniques that break down in this setting?
Welcome back to our deep dive into the proof of Kato's square root property for the generalized Stokes operator. In the previous part, we kind of set the stage. We explored those intricacies of this non-local operator and the challenges it poses to, all those traditional proof techniques. Now we're ready to, I guess, roll up our sleeves and delve into the heart of the argument.
Yes, let's examine how the researchers managed to, I don't know how they say it, tame this mathematical beast. Their strategy involves a clever interplay of a specially designed test function and those powerful non-local off-diagonal estimates we discussed earlier. The concept of a test function, it always kind of intrigues me. It's like a mathematical probe carefully crafted to reveal hidden properties of the object we're studying. What makes the test function in this paper so special?
So the test function in this proof, it needs to strike a very delicate balance.
Okay.
It has to be the gradient of a divergence-free function,
Okay.
which ensures that it aligns with the structure of the generalized Stokes operator. At the same time, it needs to capture very specific directional information, allowing us to kind of probe how the operator behaves along different axes, so to speak.
So it's like a custom-made tool designed to fit the unique contours of this operator and extract the precise information that we need.
Precisely. The researchers they start with a relatively simple function, one that captures the desired directional information, but might not perfectly align with the operator's requirements. Then they apply a series of ingenious transformations to kind of refine it, ensuring that it meets all the necessary criteria.
Could you walk us through some of these transformations? Like, what are the key steps involved in shaping this raw mathematical material into a precision instrument?
One of the first hurdles they tackle is ensuring that the function is L2 integrable.
Okay.
Meaning its energy is finite.
Okay.
And to achieve this, they multiply it by a smooth bump function, which gracefully tapers it off to zero outside a chosen region. This prevents the function from having infinite energy while still preserving its essential characteristics.
It's like sanding down the rough edges of a piece of wood, refining its shape without losing its inherent character.
Yeah, that's a great analogy. The next challenge is ensuring that the function is divergence free, which is a crucial property for working with the generalized Stokes operator. And to accomplish this, they employ a powerful tool known as the Bogovsky operator.
I remember hearing about the Bogovsky operator. It sounds almost magical.
Yeah.
Like a mathematical spell that can transform functions to meet our specific needs.
Yeah, it's a remarkable tool. The Bogovsky operator allows us to add just the right correction term to a function to make it divergence free without altering its fundamental properties. Think of it as a way to kind of fix the function so that it plays nicely with the operator.
So they've carefully sculpted this test function, ensuring it has the precise properties needed to probe the generalized Stokes operator effectively. But how does this connect to those non-local off-diagonal estimates that we discussed earlier?
So here's where where the real magic happens. By carefully analyzing the behavior of this test function at different scales and using those non-local off-diagonal estimates, the researchers can establish a crucial connection to Carlson measures.
Carlson measures. I vaguely remember encountering those in harmonic analysis. Could you refresh our memories on what they are and why they're so important in this context?
Right. So Carlson measures are a special type of measure that's defined on the upper half space,
Okay.
and they have a unique property. The weight that they assign to a region is controlled by the size of its base. It's like
Mhm.
saying the influence of a region is limited by its footprint on the ground level.
So it's a way to kind of quantify the reach or impact of different regions in this mathematical space.
Precisely. Now, the reason Carlson measures are so crucial in this proof is that they provide a bridge between the behavior of the generalized Stokes operator and a geometric property of the space itself.
I'm starting to see the connection. Are they trying to show that the generalized Stokes operator, despite its its non-local nature, somehow exhibits behavior that can be captured by these geometrically constrained Carlson measures?
Exactly. They aim to demonstrate that a certain function involving the principal part of the operator,
Okay.
which is denoted by gamma sub t. It forms a Carlson measure. This function, the modulus of gamma sub t of x, dot product with t sub 0, close modulus squared, subscript L, open parenthesis c to the d cross d is comma c to the d, close parenthesis, essentially measures the strength of the principal part at a given point
Yeah.
in the upper half space.
Right.
And if we can show that it forms a Carlson measure,
Okay.
it provides a powerful constraint on how the operator behaves at different scales.
So they're attempting to link this seemingly abstract, non-local operator to a concrete geometric property of the space. How do they go about establishing this connection? What role does the test function play in this puzzle?
So this is where the ingenuity of the proof really shines through.
Okay.
The researchers employ a very sophisticated technique called a stopping time argument
Yeah.
to analyze the test function's behavior in different scales. Imagine observing a dynamic process like the growth of a tree.
Hmm.
A stopping time argument allows us to kind of divide this process into distinct stages, marked by specific events or thresholds.
So it's like taking taking snapshots of the tree's growth at key moments,
Yeah.
capturing its evolution in a series of discrete steps.
Yeah.
How does this apply to the test function in the generalized Stokes operator?
Right. So they apply the stopping time argument to the test function, examining how it behaves as we kind of zoom in or zoom out on different regions of the upper half space, and by combining this analysis with those non-local off-diagonal estimates, they can partition the space into regions where the principal part of the operator exhibits predictable behavior.
So they're using the test function coupled with those those special rulers for measuring non-local distances to divide the space into zones where the operator plays by a specific set of rules.
Precisely, and the brilliance of the stopping time argument is that it ensures that these regions satisfy the defining property of a Carlson measure. Their influence is bounded by the size of their base. It's like demonstrating that even though the operator can have far-reaching effects,
Right.
those effects are still constrained by a certain geometric order.
This is a remarkable feat of mathematical maneuvering. They've managed to tame this wild, non-local behavior of the generalized Stokes operator, bringing it within the realm of Carlson measures. But how does this achievement lead us closer to proving Kato's square root property? What's the missing link in this puzzle?
So the connection lies in the profound relationship between Carlson measures and square function estimates, which is a powerful tool in harmonic analysis.
Okay.
Remember, our goal is to prove a square function estimate of this form. The integral from 0 to infinity of the norm of t times a, open parenthesis, 1 plus t squared a, close parenthesis, to the -1, u close norm square, subscript L squared dt over t is approximately equal to the norm of the gradient of u squared subscript L squared.
Okay.
This estimate tells us that the roughness of the square root of the operator, which is a, it can be controlled by the smoothness of the function u, represented by its gradient.
Right. It's like saying that the complexity of the square root is somehow tamed by the regularity of the function it's acting upon. But how do Carlson measures enter this picture?
So the key insight is that Carlson measures, they provide a means to control certain types of square function estimates. They allow us to bound the integral of a function against a Carlson measure by the norm of a related function.
So they've established this intricate connection between the operator and Carlson measures, and now they're leveraging that connection to gain control over the square function estimate. That lies at the heart of Kato's property.
Exactly. They demonstrate that the square function involving the operator A can be bounded by the integral of a related function against the Carlson measure they've painstakingly constructed. And by skillfully crafting the test function and employing that stopping time argument, they can control this integral in a way that directly leads to the desired square function estimate.
It's a truly impressive display of mathematical ingenuity.
Right.
They've woven together this complex tapestry of ideas from different areas of mathematics,
Absolutely.
carefully connecting the dots to make significant progress towards proving Kato's property for this elusive non-local operator.
Indeed. And while we've covered a lot of ground in this part, there's still much more to explore. In the final part of our deep dive, we'll delve into the concept of holomorphic dependency and examine how the researchers established this fascinating property for the generalized Stokes operator.
I'm eager to uncover the final pieces of this mathematical puzzle. This deep dive has already revealed so much about the power and beauty of abstract reasoning.
Yeah.
And I can't wait to see how it all comes together in the end. Welcome back to the final part of our deep dive into the proof of Kato's square root property for that generalized Stokes operator. We've journeyed through all the intricate challenges posed by non-locality, witnessed the construction of that specialized test function, and explored that that fascinating world of Carlson measures. Now we arrive at a concept that might seem a bit mysterious at first glance. Holomorphic dependency.
Yeah.
Yeah.
Holomorphic dependency, it kind of adds another layer of intrigue to this already fascinating mathematical landscape. You know, it might sound like a highly technical term, but at its core, it really reflects a certain I guess smoothness or predictability in the behavior of the operator as we vary its parameters.
I always appreciate when we can kind of connect these abstract mathematical ideas to a more intuitive sense of how things behave.
Right.
When you say smoothness in this context, what exactly are we varying, and what's behaving smoothly as a result?
So in this case, we're focusing on the coefficients of the generalized Stokes operator represented by the matrix mu.
Okay.
Remember, these coefficients encode information about the fluid's properties, like its viscosity.
Okay.
What the researchers demonstrate is that as we slightly tweak these coefficients, the square root of the operator changes in a smooth, predictable way.
So it's like saying that our mathematical model of the fluid is robust.
Exactly.
Small changes in the fluid's characteristics, like its viscosity, don't cause any sudden jumps or chaotic behavior in the operator's square root.
Precisely. In mathematical terms, they show that the map from the coefficients mu to the square root of the operator, which is denoted as a submu, is holomorphic. And this property has significant implications for both theoretical analysis and practical applications.
Yeah, I can see how that would be valuable.
Right.
On the theoretical side, it allows us to explore how the operator behaves under different conditions without worrying about unpredictable jumps or discontinuities.
Yeah.
It's like having a reliable control knob for for our mathematical experiments.
Exactly. And on the practical side, this holomorphic dependency gives us, confidence in numerical simulations. A lot of numerical methods rely on, on approximations, and knowing that these approximations change smoothly with the coefficients ensures, stability and accuracy in our results.
It's like having a guarantee that our computational tools won't suddenly, break down if we make slight adjustments to the fluids parameters.
Right.
But how do the researchers actually prove this holomorphic dependency? What techniques do they employ to establish this smooth relationship?
They cleverly combine tools from complex analysis and operator theory. A key ingredient in their proof is a representation of the operator's square root, known as the Balakrishnan formula.
Okay.
And this formula essentially expresses the square root as an integral involving the operator itself.
That's intriguing. It seems like they're transforming a complex operation, finding that square root into an integral.
Right.
Which is often easier to analyze and manipulate.
Exactly.
Does this transformation make it easier to see how the square root changes as we vary those coefficients?
Yes, the Balakrishnan formula provides a framework for studying the subtle changes in the square root as we perturb the coefficients. Yeah. And the researchers carefully analyze this integral, utilizing their knowledge of the operator's properties, including those non-local off-diagonal estimates, and the fact that coefficients mu are bounded. And this careful analysis allows them to demonstrate that the square root changes holomorphically with respect to mu.
It sounds like a delicate dance between different areas of mathematics, weaving together insights from complex analysis, operator theory, and even those non-local estimates that we discussed earlier.
It is. It's a beautiful example of how seemingly disparate mathematical concepts can intertwine to reveal deeper truths.
Yeah.
And this holomorphic dependency isn't just a theoretical curiosity. It has a very concrete consequence known as local Lipschitz continuity.
Lipschitz continuity. That rings a bell. Doesn't it relate to how much a function can change over a given interval?
Yes, Lipschitz continuity essentially tells us that the rate of change of a function is bounded. In this context, it means that the difference between the square roots of two operators with slightly different coefficients is bounded by the difference between the coefficients themselves.
So it reinforces the idea that small changes in the fluid's properties lead to proportionally small changes in the operator's square root. No sudden jumps or unpredictable behavior.
Precisely. And this property is incredibly valuable for both theoretical analysis and numerical computations. Yeah. It provides a sense of stability and predictability, allowing us to explore the behavior of the operator with confidence.
As we conclude our deep dive into this remarkable proof, I'm struck by the ingenuity and elegance of the researchers' approach. They've tackled a complex non-local operator property that's notoriously challenging to prove, and unveiled this hidden layer of smoothness and predictability in its behavior.
Absolutely. This paper is a testament to the power of mathematical reasoning, showcasing how abstract tools and concepts can illuminate our understanding of the physical world.
Well, thank you for guiding us through this intricate mathematical landscape. I'm sure our listeners, like myself, have gained a newfound appreciation for the beauty and depth of mathematics and its ability to reveal hidden order in seemingly complex phenomena. Until next time, keep those mathematical minds engaged. Welcome back, everyone. Ready for another deep dive?
Always.
Today we're tackling a paper that really pushes the boundaries of fluid mechanics.
Ooh, I'm intrigued.
It's all about Kato's square root property, but with a twist. We're not dealing with your everyday elliptic operators here.
So non-local, I'm guessing.
You got it. It's the generalized Stokes operator and its non-locality that makes this paper by Luca Hart and Patrick Tolstorff so fascinating.
Yeah, the classic Stokes operator is already a challenge, but adding non-locality takes it to a whole new level.
So before we get lost in the mathematical weeds, let's start with the basics. What exactly is the generalized Stokes operator?
Well, formally it's defined as AU, line duve plus AAA plus a C is our pressure term.
Okay, so we've got representing velocity. Our coefficients, think of them like viscosity and fluid dynamics, and what is our pressure term?
Precisely. And it's that the gradient of the pressure that brings in the non-locality.
Okay.
It means that what's happening at a particular point is influenced by what's happening further away, not just its immediate surroundings.
So it's not just about local interactions anymore.
Exactly. And that makes things much trickier mathematically.
So how does Kato's square root property even fit into all of this?
Well, Kato's question way back in the 1960s was about characterizing the domain of the square root of certain operators.
Domain meaning.
The set of functions that you can plug into the square root and still get a sensible result.
Got it.
And we know this property doesn't hold for all operators. There are those famous counterexample,
Why?
Lyons and McIntosh.
Right. But it has been proven for certain types, like elliptic operators.
Exactly. That was a big breakthrough back in 2002.
Aye.
A whole team, actually. Auscher, Hofmann, Lacey, McIntosh, and Tchamitchian.
So this paper is building on that legacy, but tackling a much more difficult non-local operator.
Precisely. And their big result is that the generalized Stokes operator does indeed possess the Kato square root property.
You mean?
It means its domain can be described by divergence-free H1 vector fields.
Divergence-free.
Yeah, because we're dealing with incompressible fluids, remember, their volume doesn't change under pressure.
Right, that's baked into the very definition of the Stokes operator.
Exactly.
Okay, so they've nailed down this square root property for this complex non-local operator?
Yep, but they go even further.
How so?
They also explore how the square root of this operator changes when you tweak those viscosity coefficients, the oins.
So they're not just looking at a static property, but how it behaves under changing conditions.
Exactly. And what they find is that the square root of the operator depends holomorphically on these coefficients.
Holomorphically.
It basically means it changes smoothly. When the coefficients vary, the square root of the operator also varies in a smooth, predictable way.
So it's not going to jump around erratically.
Nope. It's all very well behaved.
That's reassuring.
And this leads to a very practical consequence, a Lipschitz estimate for the square root of the operator.
Lipschitz.
It means that small changes in those viscosity coefficients result in proportionally small changes in the square root of the operator.
So it's like a stability property.
Yeah.
The system isn't going to go haywire if there are slight variations in the fluid's viscosity.
Exactly. It's all very controlled and predictable.
And this holds true even if we focus on symmetric coefficients, which is a common simplification in fluid models.
Precisely. So even in those simplified cases, we still get this valuable Lipschitz estimate.
Wow, this is already getting pretty deep.
It is, but we're just scratching the surface.
I'm ready to dive deeper.
All right. Let's get into the nitty-gritty of their proof and see how they tackled this beast of a problem.
Lead the way.
Now, their proof is quite a journey. It all starts with the L2 theory of the generalized Stokes resolvent.
Resolvent.
Think of it like the inverse of the operator. It helps us understand how the generalized Stokes operator behaves in a certain mathematical space.
Okay, so it's a tool to analyze the operator itself.
Exactly. They establish some fundamental L2 estimates for this resolvent.
Meaning?
These estimates tell us that the resolvent is well behaved. It doesn't cause any unexpected mathematical hiccups.
So it's like laying the groundwork, making sure everything is in order before they proceed.
Precisely. And these L2 estimates are crucial for what comes next. The non-local off-diagonal estimates.
Ah, yes. Those were a key innovation you mentioned earlier.
Exactly. They are the heart of their approach to handling the non-locality.
Can you remind us again how those non-local estimates work?
Sure. The basic idea is to break down the solution to the generalized Stokes equation into a series of terms.
Okay.
Each term represents the influence of a different region of space.
So they're isolating the effects of what's happening in one place versus another.
Exactly. And the clever part is they can then analyze each term and show that its influence decays in a very specific way.
How so?
It decays polynomially. The further away you get, the weaker the influence becomes, and they can describe this decay with a polynomial function.
I see. So that's how they quantify the non-local effect.
Precisely. And that polynomial decay is what makes their non-local off-diagonal estimates work. It allows them to adapt those traditional proof techniques that rely on measuring the influence of distant regions.
Clever. Now, you also mentioned that they reduced the problem to a square function estimate.
Right. Square function estimates are a powerful tool in this area of mathematics.
What do they tell us?
They help us measure the smoothness of an operator. In this case, the square function estimate helps them gauge how smooth the generalized Stokes operator is.
Smoothness.
It's a way to describe how well-behaved the operator is, how much it fluctuates or jumps around.
Okay, so a smooth operator is a well-behaved operator.
Exactly. And their key insight is that if they can prove this square function estimate holds, then the Kato square root property follows naturally.
So it's like a domino effect. Prove the square function estimate and the Kato property falls into place.
Precisely. Now, to prove this square function estimate, they use a technique called principal part approximation.
Principal part approximation.
It involves splitting the operator into two parts, a principal part and a remainder term.
Divide and conquer.
Exactly. The principal part captures the essential behavior of the operator, while the remainder is like the leftover bits.
Okay, so they simplify things by focusing on the core behavior.
Precisely. And for this principal part, they introduce a clever concept called dyadic averaging.
Dyadic averaging.
Imagine dividing the space into a grid of cubes.
Okay.
Dyadic averaging involves averaging the function over each of these cubes. It's a way to smooth out the function and get a simpler representation.
So they're simplifying the principal part even further by averaging it over these cubes.
Exactly. And the key result here is that if they can prove a certain estimate for this principal part, then the square function estimate for the principal part will hold.
What kind of estimate are we talking about?
A Carlson measure estimate.
Carlson measures again. They seem to pop up everywhere in this proof.
They're a fundamental tool in this area of mathematics. They help us control the behavior of functions and operators.
So this Carlson measure estimate is crucial for proving the square function estimate for the principal part.
Exactly. And to tackle this Carlson measure estimate, they bring in another clever tool, a TB-type test function.
A test function.
Yes. It's a specially designed function that helps them probe the properties of the principal part.
What makes this test function so special?
It has to satisfy three key conditions. First, it must be a gradient of a divergence-free H1 function.
Divergence-free, because we're dealing with incompressible fluids.
Exactly. Second, it must have a certain average value over those dyadic cubes we talked about.
Okay.
And third, it must satisfy a specific Carlson measure estimate.
So it's a highly tailored tool designed for this specific task.
Precisely. Constructing this test function is a delicate process involving bump functions and a technique called a Bogovsky correction.
A Bogovsky correction.
It's a way to adjust the function so that it becomes divergence-free while still preserving its other important properties.
So it's like fine-tuning the test function to fit their exact needs.
Exactly. Once they have this TB-type test function, they can finally tackle that Carlson measure estimate for the principal part.
How do they do that?
They use a combination of techniques, including a stopping time argument and a John-Nirenberg lemma for Carlson measures.
Those sound pretty advanced.
They are, but the key takeaway is they managed to bound the Carlson measure of the principal part using the properties of their carefully constructed test function.
So the test function acts as a bridge to prove the Carlson measure estimate for the principal part.
Exactly. It's a beautiful example of how mathematicians use cleverly designed tools to crack complex problems.
Okay, they've conquered the principal part. What about that remainder term you mentioned earlier?
Handling the remainder term is a bit simpler. They use a combination of those non-local off-diagonal estimates, some smoothing techniques, and quadratic estimates to show that it also satisfies the desired square function estimate.
So different tools for different parts of the operator.
Right. They've carefully chosen the right techniques for each piece of the puzzle.
And once they've shown that both the principal part and the remainder term satisfy the square function estimate, they've essentially proven the entire estimate.
Exactly. They combine these pieces to obtain the full square function estimate for the generalized Stokes operator.
Which in turn implies the Kato square root property.
Precisely. It's a chain reaction of mathematical logic.
We've covered a lot of ground here. L2 theory of the resolvent non-local off-diagonal estimates, square function estimates, principal part approximations, Carlson measures TB-type test functions. It's been quite a ride.
It has. But we're not done yet. We still need to delve into that holomorphic dependency of the square root of the operator on the viscosity coefficients.
Right. You mentioned that leads to some interesting consequences. Let's explore that next. Okay, so back to that holomorphic dependency. What's that all about again?
Remember those viscosity coefficients, the Waynes? Well, in real-world fluids, those can change. Holomorphic dependency means that as those coefficients change, the square root of the operator also changes, but in a smooth, predictable way.
Smooth meaning no sudden jumps or erratic behavior.
Exactly. It's all very well behaved.
Hmm.
And to prove this, they use a clever trick from complex analysis.
Oh.
They represent the square root of the operator using something called a contour integral in the complex plane.
Contour integrals. I vaguely remember those from my complex analysis days. How do they apply here?
A contour integral is a way to evaluate a complex function along a path in the complex plane. By carefully choosing the path and using the properties of holomorphic functions, they can show that the square root of the operator depends holomorphically on those viscosity coefficients.
So complex analysis to the rescue.
It's a great example of how different areas of math can come together to solve problems. Now, this holomorphic dependency leads to a very important result, that local Lipschitz property we talked about.
Right, the one from corollary 1.4. Remind me what that tells us again.
It basically says that if we make a small change to the viscosity coefficients, the corresponding change in the square root of the operator will also be small, and we can even quantify how small.
So it's another way to express the stability of the system. Even if those viscosity coefficients fluctuate a bit, everything stays under control.
Precisely. And what's remarkable is that this Lipschitz property holds even if we restrict ourselves to symmetric viscosity coefficients, which is a common assumption in fluid models.
So even in simplified scenarios, we get this valuable insight.
Exactly. It allows us to analyze how small variations in a fluid's properties like temperature or composition can impact its overall flow behavior. That's powerful stuff.
Absolutely. So we've gone from Kato's question about the square root of operators to this deep dive into the generalized Stokes operator and its non-local nature. We've explored L2 estimates, non-local off-diagonal estimates, square function estimates, principal approximations, Carlson measures, TB-type test functions, holomorphic dependency, Lipschitz properties. It's been a whirlwind tour of some pretty advanced mathematics.
It has, but I think it highlights the beauty and power of math to unravel the complexities of the physical world.
Definitely. And the fact that this paper focuses on the whole space, while real fluids are often confined within boundaries like pipes or containers, just shows how much more there is to explore.
Exactly. This is just the beginning. There are so many exciting avenues for future research.
Well, this has certainly been a fascinating deep dive. Thanks for guiding us through it.
My pleasure. Always happy to delve into the world of fluid mechanics.
And to our listeners, thanks for joining us on this mathematical adventure. Until next time, keep exploring. Welcome back to the show. Today we're doing a deep dive on a really neat proof by Hart and Tolksdorf.
Yeah.
It's about Kato's square root property
Okay.
for the generalized Stokes operator.
Interesting.
Now, I know you're no stranger to this kind of math,
Right.
but what makes this paper really fascinating is the way they handle the non-locality of this operator.
Yeah, the non-locality, that's always a tricky bit.
Exactly. They use these really ingenious non-local off-diagonal estimates, and we're going to unpack all that.
Sounds good.
So, first things first, let's recap the Kato square root problem.
Okay.
Essentially, the question is,
Yeah.
if you have a maximal accretive operator,
Uh-huh.
and I know you know what that means,
I do.
does the domain of its square root line up with the domain of the form that generates it?
Right. And it's not just some theoretical thing. It has real implications, like for understanding how these operators behave.
Absolutely. It's
Yeah.
all tied up in those energy estimates that are like the foundation of so much analysis.
For sure.
A good example is the Laplacian operator, right?
Yeah.
Nice and well-behaved. It's
Yeah.
been a while since we figured out its square root property.
Yeah.
But then you throw the generalized Stokes operator into the mix
And things get a lot more interesting.
because of that non-locality.
Exactly.
The generalized Stokes operator, it pops up when you linearize the equations for how non-Newtonian fluids flow.
Right.
And unlike the Laplacian,
Yeah.
its behavior at one point can be affected by things happening way over there.
That's the non-locality for you.
So how does that non-locality actually show up in the math of the generalized Stokes operator?
Yeah.
What makes it so hard to work with?
Well, okay, so formally, the generalized Stokes operator is given by one nabla plus nabla phi,
Okay.
where the coefficients, the nabla, those represent the fluid's viscosity. And we assume they're bounded, measurable, and satisfy a Gording inequality.
Right. The Gording inequality, that basically ensures some kind of ellipticity, doesn't it?
Precisely. A weaker version than usual, but yeah. Now, the tricky part is that divergence-free condition, text divo.
Okay.
It restricts the domain of the operator to those divergence-free vector fields. And that's what brings in the non-locality.
I see. So we can't just look at things locally.
Nope. You got to account for all those long-range interactions.
Which brings us back to those non-local off-diagonal estimates you were talking about.
Yeah.
Seems like that's the key to Hart and Tolksdorf's approach.
It is.
So what's the intuition behind them? How do they help us get around the non-locality?
Okay, so in the classical setting, when you're dealing with local operators,
Right.
we often use these off-diagonal estimates to prove the square root property. They basically tell you how the resolvent of the operator decays as you move away from a point.
Okay.
But with this generalized Stokes operator,
Yeah.
those traditional estimates just don't hold up.
Because of the non-locality, right. We can't expect things to decay so nicely anymore.
Exactly. So Hart and Tolksdorf, they came up with these brilliant non-local off-diagonal estimates. Instead of directly looking at how the resolvent decays, they consider how certain expressions involving the resolvent and a special test function decay.
Interesting.
It's really clever.
And they get a polynomial order of decay for these expressions.
They do. It's remarkable.
How did they even derive those estimates? It sounds pretty intense, mathematically speaking.
It is. They use an iterative procedure, carefully using the structure of the operator and the properties of those coefficients. Their main result is in proposition 2.5.
Right.
They lay out the exact form of these non-local off-diagonal estimates. It's a bit of a complicated formula.
I can imagine.
But the main idea is this. Even if the resolvent itself doesn't decay neatly, certain combinations with the right test functions do show polynomial decay.
Okay, so you've got these non-local off-diagonal estimates. Now what? How do they fit into proving the square root property?
That's where the square function estimate comes in. It's a standard trick, even when things are non-local. You show that the square root property is equivalent to a particular square function estimate.
Like in equation 3.1.
Exactly. Showing the square root property comes down to showing that the 2 norm of the square function of panobla 1 plus T2A 1P text divest phi is controlled by the 2 norm of $5.
Right.
And then what Hart and Tolksdorf do is connect the square function estimate to quadratic estimates for operators with a bounded HNFD calculus.
Okay.
They use a key theorem from McIntosh for that.
I see. So they're bringing in tools from harmonic analysis now.
Exactly. It's brilliant.
So they've established these powerful non-local off-diagonal estimates. They've linked the square root property to this square function estimate. What's their next move?
Well, the next brilliant step is introducing this concept of the principal part of the operator.
Okay.
It's defined in definition 4.3, and it basically involves approximating the operator in a kind of averaged way. This approximation helps to simplify things, lets them focus on the really crucial parts of the operator.
So how does this principal part approximation actually help them prove that square function estimate? It seems like they're breaking down the problem into smaller, more manageable pieces.
That's exactly it. The principal part approximation is key for proposition 4.5. That's where they show that the square function estimate boils down to proving a Carlson measure estimate.
Carlson measures. Now, things are getting really interesting. How do those connect to the principal part of the operator?
Well, that's the story for part 2 of our deep dive.
Oh, good.
So remember where we left off. We need to prove that a certain measure involving the principal part of the operator is a Carlson measure.
Right, Carlson measures.
Quick reminder for anyone who needs it.
Yeah.
They're measures on the upper half space, math plus 1 plus $,
Okay.
and they satisfy a special growth condition.
Right.
Really fundamental in harmonic analysis, especially for boundary value problems.
Okay, so how do these Carlson measures help us prove the square root property for the generalized Stokes operator? It seems like we've wandered off into a totally different area of math.
Well, the connection is this. Carlson measure estimates can control certain integral operators, which are connected to that square function estimate we're trying to prove.
That's it.
Now, to get the Carlson measure estimate, we need Hart and Tolksdorf use this really clever strategy.
Okay.
They construct a special test function.
What kind of test function?
It's called a TB type test function.
TB theorems, right. I remember those.
Yeah.
Powerful stuff for proving boundedness of singular integral operators.
Exactly. But how do they work here, especially with the non-locality of the generalized Stokes operator?
Good question.
Well, they need this test function to do two things.
Okay.
First, it needs to be the gradient of a divergence-free vector field.
Right, to connect back to the generalized Stokes operator.
Exactly. Second, it needs to be aligned with the direction of the unit matrix, the one that maximizes the norm of that principal part of the operator.
So it has to capture those key features of the operator and its principal part. But how do you even build a test function like that?
Well, they start with a kind of guess, an ansatz.
Ah,
It involves the gradient of the resolvent of the operator.
okay.
This makes sure the test function is a gradient, but it doesn't necessarily make it divergence-free. And it might not be aligned the right way either.
So they need to tweak it. What's the trick?
They use the Bogofsky operator.
Okay.
It's this great tool for correcting the divergence of a vector field without messing up other important properties.
Interesting.
So they combine the resolvent with a carefully chosen Bogofsky correction, and bam, they've got their test function.
Wow, that's impressive. Combining the resolvent with the Bogofsky correction to create a test function that's both divergence-free and aligned with the principal part's direction shows how well they understand these operators.
For sure. And this carefully made test function, plus a stopping time argument, plus the John Nirenberg lemma for Carlson measures,
Okay.
they all come together to prove a directional Carlson measure estimate. It's in proposition 5.4.
Right.
Basically, it says we've got a Carlson measure estimate when we restrict the principal part of the operator to a specific cone.
And we can cover all the possible directions for the principal part with just a bunch of cones.
Nice.
So we could piece together those directional estimates to get a global Carlson measure estimate.
Precisely. And that leads us to the square function estimate we were after, which finally gives us the square root property.
It's like all these math ideas working together in perfect harmony.
Right.
They've combined functional analysis, harmonic analysis, even some geometry to get this elegant result.
It's beautiful, but there's more. Kato wasn't just interested in proving the square root property. He wanted to know how the square root depends on its coefficients. And guess what? It turns out that dependence is holomorphic.
Holomorphic. Now we're talking complex analysis.
It's amazing how this proof uses so many different mathematical tools.
I know.
But that's how math works, right? It's all connected. And this holomorphic dependency means that the square root of the generalized Stokes operator changes smoothly with respect to its coefficients.
So if we slightly change the coefficients, the square root changes smoothly too.
Exactly. It's stable under perturbations, which is really important for real-world applications.
Because in the real world, those parameters are often uncertain or changing.
Right. And they actually quantify this stability with a local Lipschitz estimate in Corollary 1.4. It shows how much the square root changes when you tweak the coefficients a little bit.
That's a really powerful result. It shows how abstract math can help us understand real physical phenomena. But how did they prove this holomorphic dependency?
They used a combination of cool techniques. They start with the Balakrishnan representation for square roots, which gives you an integral representation of the square root. Then they use Taylor's theorem to expand the square root in terms of its coefficients. Finally, they use Schwarz's lemma from complex analysis to control the remainder term in that Taylor expansion. That shows the dependency is holomorphic.
Wow, they've managed to combine operator theory, complex analysis, and even some calculus to reveal this really elegant property of the generalized Stokes operator. It's impressive how they've woven together all these different ideas.
It really is. And it shows how powerful mathematical abstraction can be for understanding complex things. It also opens up some really interesting questions for further research, like can we extend this holomorphic dependency result to other types of non-local operators? And what other applications could come from understanding how these square roots behave under perturbations?
So we've really dug deep into this proof, haven't we? Starting with that whole challenge of non-locality.
Yeah.
Those long-range interactions that make the generalized Stokes operator such a pain to work with.
Yeah, and those usual off-diagonal estimates, the ones that work so well for elliptic operators, they just don't cut it here. Hart and Tolksdorf had to come up with a whole new toolbox to tackle this.
And those non-local off-diagonal estimates they came up with, those were a game changer. It's amazing how they squeezed out that polynomial decay from those expressions with the resolvent.
It's pretty clever. And that polynomial decay was key, right? It let them connect the square root property to a square function estimate, which they then linked to quadratic estimates for operators with a bounded H and infinity calculus. Lots of moving parts.
And then there was that principal part, approximation. Talk about a smart way to simplify things. It let them zero in on the important parts of the operator, reducing the problem to a Carlson measure estimate. Genius.
Carlson measures are a powerful tool, no doubt. And the way they use them, constructing that TB-type test function, elegant.
Combining the resolvent with a Bogofsky correction to make sure it was both divergence-free and aligned the right way.
Yeah.
Really impressive.
Shows a deep understanding of these operators.
Their command of all those different areas of math is inspiring. Functional analysis, harmonic analysis, complex analysis, even a bit of geometry all woven together.
Yeah, they pulled it all together beautifully. And it's not just about the technical skill, right? This result has some big implications for how we think about non-local operators. Knowing that the square root depends on the coefficients in a holomorphic way opens up all sorts of possibilities for analysis and applications.
Absolutely. Knowing it's stable under those little perturbations is a huge deal when you're working with real systems where things are always a bit uncertain or in flux. It makes you wonder, what other cool stuff is hiding in that holomorphic dependency? What else can we learn?
Tons of potential for future research there. Could this kind of dependency be a more general thing with non-local operators? What new applications could we find if we really understand how these square roots behave when you tweak things?
Such great questions. This deep dive has been a real testament to the power of mathematical abstraction. It's amazing how all these seemingly different areas of math can come together to solve tricky problems. And it reminds us that there's always more to discover, more connections to find, more insights to gain. Thanks for joining us, and until next time, keep those mathematical minds working. Welcome back to the Deep Dive. Today, we're going to be looking at some fascinating new research on the Kato square root property.
Okay.
Specifically, how it applies to the generalized Stokes operator. Now, you're all familiar with the Kato square root problem.
Of course, yeah.
Does the domain of the square root of an operator
Right.
always coincide with the domain of the form it's derived from?
And as we know, it's not a simple yes or no answer. I mean,
Right.
Lyons and McIntosh really showed us that sometimes it just doesn't hold the square root property.
And that's what makes this paper so intriguing. They've tackled this square root property for the generalized Stokes operator,
Right.
which, as you know, is a key player when we're talking about fluid mechanics, especially when we're dealing with non-Newtonian fluids.
Yeah. And what's really interesting here is that the Stokes operator, unlike so many of the elliptic operators that we're used to working with, it's non-local. And that kind of throws a wrench in the works, because one of the standard tools that we use in these proofs, off-diagonal estimates, sort of rely on that locality.
So they had to come up with some sort of clever workaround
Exactly.
to deal with that non-locality.
Exactly.
Okay.
But before we get into the really detailed approach, let's just set the stage a little bit. So the paper defines the generalized Stokes operator formally as a u colon equals negative divergence mu, gradient of u plus gradient of phi, divergence of u equals 0.
Okay, let's break that down. So we've got A representing the operator itself.
Right.
And then is our velocity field.
That's right, exactly.
Okay.
And then we have mu, which is representing our coefficients, which
Yeah.
essentially describe the fluid's viscosity.
Okay.
And then grad is the gradient of the velocity field.
Okay.
It's essentially capturing how the velocity is changing in space.
Mm-hmm.
And then phi is our pressure term.
Okay.
And then that last part, divergence of u equals 0, that's our incompressibility condition.
Right, making sure that the fluid's volume doesn't change
Exactly.
under pressure.
Yeah, precisely. Now, the main challenge the paper really tackles is proving that the domain of the square root of this operator, so square root of A, is the same as the space of divergence-free H1 vector fields.
So what they're trying to show is, if you have a divergence-free vector field whose gradient is square integrable,
Exactly.
then you can apply the square root of the Stokes operator to it, and the result will still be a well-behaved function
Exactly.
in that same space.
Exactly. Yeah. And theorem 1.2 in the paper is really where they sort of nail this down. They confirm the square root property for the generalized Stokes operator. And crucially, they provide an estimate relating the norms of the gradient of the velocity field and the square root of the operator.
And this is where these non-local off-diagonal estimates come in, right? They have to develop this new set of tools to deal with the non-locality of the Stokes operator.
Yeah. So traditional off-diagonal estimates sort of rely on the operator being local,
Okay.
meaning its effect at a point is only influenced by what's happening in a small neighborhood around that point. But the Stokes operator doesn't really play by those rules. Its effect can be felt far away from the point of action.
So how did they get around that?
That's where proposition 2.5 comes in. So they establish these non-local off-diagonal estimates, but with a really crucial addition, polynomial decay.
Okay.
And this decay factor is vital because it ensures that the estimates are strong enough to actually carry through the rest of the proof.
Okay, so they've tackled the non-locality issue. What's the next step in their strategy?
So what they do is they actually connect the square root property to something called a square function estimate.
Okay.
It's a little technical, but essentially they show that if they can prove that this particular estimate holds, then the square root property must also be true.
And I see in equation 3.1 in the paper, that's where they lay out this
Exactly.
the square function estimate.
Yeah, and it's worth taking a closer look at it. It states that the integral of the square of the norm of a specific function involving the operator applied to our velocity field should be comparable to the square of the norm of the gradient of u. Okay. So essentially what it's doing is it's relating the energy of the operator applied to the energy of the gradient of u.
So if they can prove that that relationship holds, then the square root property follows.
Exactly.
Okay.
And to tackle this square function estimate, they introduce a really neat technique called principal part approximation.
Okay, this sounds interesting. What's the idea behind this principal part approximation?
The idea is to sort of approximate the operator in a way that allows them to use existing tools but still capture its essential behavior.
Okay.
And so they introduce something called the principal part. It's denoted by gamma sub t, which plays a central role in this approximation.
I see in definition 4.3, that's where they really dive into what gamma sub t actually is.
Yeah.
And it looks pretty involved.
It is, but the key takeaway is that it's really capturing the dominant behavior of the operator at different scales.
Yeah.
You can kind of think of it as like a way to zoom in and out, focusing on the operator's action at different levels of detail.
Okay. Yeah. And then proposition 4.5 really lays out their plane of attack.
Exactly.
Show that a certain measure involving gamma sub t is a Carlson measure.
Right.
And you've got your square root property.
Exactly. And to prove this Carlson measure estimate, they construct a special, what's called a TB type test function.
Okay.
It's a very custom designed tool that helps them to kind of probe the behavior of the operator.
So for those of us who haven't encountered them in a while, remind us, what exactly is a Carlson measure?
Essentially, a Carlson measure is a way of measuring the concentration of a measure near the boundary of a domain.
Okay.
And it's defined on the upper half space. And the key property is that the measure of a box sitting on the boundary shouldn't grow too fast compared to the size of its base.
And definition 5.1 in the paper really lays that out precisely.
Exactly.
It says a measure on this upper half space is a Carlson measure if the measure of any of these boxes is bounded by some constant times the measure of its base down on the boundary.
Precisely. And that constant is what we call the Carlson norm.
Okay.
And so the smaller the norm, the less concentrated the measure is near the boundary.
Okay.
So to prove the Kato property for this generalized Stokes operator, what they need to demonstrate is that a particular measure constructed from their principal part, gamma sub t, satisfies this Carlson condition.
Got it. So how do they go about constructing this special test function?
Well, it has to actually satisfy two tricky constraints simultaneously.
Okay.
First, it needs to be the gradient of a divergence-free H1 function.
Okay.
Which, of course, ensures that it plays nicely with the Stokes operator.
Right.
And second, it has to be designed to kind of point in a very specific direction, which is crucial for the sectorial decomposition that they use in the proof.
So it's like a highly specialized arrow that's helping them navigate through complexities of the operator.
Right.
And its behavior.
Right.
I see they introduced the Bogosky operator at this point. What's its role in all this?
So the Bogosky operator is a tool that guarantees the existence of a vector field with a given divergence.
Okay.
And in this case, they use it to make sure that their test function is indeed divergence-free, so it satisfies that first crucial constraint.
Ah, I see. So they're essentially using the Bogosky operator to enforce that connection to the Stokes operator.
Exactly. Exactly.
Okay. And then proposition 5.5 really lays out all the properties of this ingeniously constructed test function.
Right. And it has to satisfy, specific bounds and conditions to make sure that it's powerful enough to tackle the problem.
Right.
And this is really where the technical heavy lifting begins.
Okay.
They need to show that a specific measure involving this test function and the principal part, gamma sub t, is indeed a Carlson measure.
And this is where the stopping time argument and the John Nirenberg lemma come into play, right? These are some pretty powerful tools from harmonic analysis.
Exactly. So lemma 5.6 is where they apply the stopping time argument.
Oh.
And essentially what it does is it breaks down the base of our Carlson box,
Oh.
the cube Q, into smaller subcubes where certain good properties hold.
Okay.
You can kind of think of it like strategically dividing a region to make it easier to analyze.
So they're cleverly partitioning the problem
Exactly.
to get a better handle on the behavior of the measure.
Precisely. And this partitioning ensures that a significant portion of the original cube, at least some fixed percentage, is covered by these good subcubes where we have strong control over the principal part.
Okay, right.
And then lemma 5.7, the John Nirenberg lemma, swoops in to help them connect the behavior on those good subcubes to the rest of the cube. You got it. The John Nirenberg lemma is a powerful tool that links the measure of our good set and the behavior of the measure on the complement of this set. The stopping time argument already gave us the first property.
Right.
A substantial portion of the cube is good, and the directional Carlson estimate from proposition 5.4 helps control the measure on the complement.
It's amazing how they weave together all these different tools and techniques. So they've proven that the measure associated with the principal part truly is a Carlson measure.
Yes.
What happens next?
With that Carlson measure estimate, they've really checked off all the boxes needed to prove the square root property for the generalized Stokes operator.
Theorem 1.2, complete.
Yeah.
But they don't stop there, do they?
No, they do.
There's more to uncover in this paper.
You're right. They go on to explore a fascinating consequence of their proof, and that's holomorphic dependency.
Okay.
It essentially means that the square root of this operator depends smoothly in a very specific mathematical sense on the viscosity coefficients that we talked about earlier.
So if those coefficients, those mu's, change slightly, the square root of the operator changes in a predictable, smooth way.
Exactly.
Okay.
And theorem 1.3 really formally states this holomorphic dependency.
Yeah.
It's a real testament to the power of their proof technique that it reveals this additional structure that might not have been obvious at first glance.
And corollary 1.4 takes this abstract mathematical notion and gives us a concrete way to quantify it, right?
Precisely.
Okay.
The corollary provides a Lifshitz estimate showing that small changes in those coefficients lead to proportionally small changes in the square root of the operator.
So it's not just a theoretical curiosity. It has implications for how we understand and model these fluids.
Absolutely.
Knowing that the operator behaves predictably under small perturbations is valuable.
It is, absolutely. This holomorphic dependency really gives us a deeper insight into the stability of the system. It tells us that the mathematical framework is robust, even in the face of real-world variations and uncertainties.
It's like they've shown us that the math not only works, but works in a way that's relevant and applicable to real-world scenarios.
Exactly.
This deep dive has been a whirlwind tour of some incredibly intricate mathematics.
It has.
What stands out to you as the most insightful aspect of this paper?
You know, for me, it's the way they tackled the non-locality of the generalized Stokes operator.
Mm-hmm.
Their use of these non-local off-diagonal estimates and the construction of that TB-type test function are truly innovative.
They had to develop new tools and techniques to deal with this challenge.
They did.
And in doing so, they've opened up new avenues of research.
Absolutely.
Who knows what other non-local operators might be hiding similar secrets?
It's an exciting thought.
Yeah.
And, you know, this unexpected connection to holomorphic dependency just adds another layer of intrigue. It makes you wonder what other hidden structures and connections are just waiting to be discovered in these seemingly abstract mathematical concepts.
Well, I think we've given our listeners plenty to ponder today.
I think so, too.
It's been a real deep dive into the fascinating world of the Kato square root property and the generalized Stokes operator.
Yeah.
And we've seen how a seemingly abstract mathematical concept can have profound implications for our understanding of complex systems.
Absolutely.
We've only scratched the surface.
We have.
I encourage everyone to explore the source material, delve into the details of the proofs, and see what other insights they can glean.
Couldn't agree more.
Who knows what mathematical treasures you might uncover.
Indeed.
Thanks for joining us on this deep dive.
It's been a pleasure.
Until next time, keep exploring, keep questioning, and keep pushing the boundaries of mathematical understanding.